All right. Hi, everyone, and thank you all for joining us in today's webinar. We're going to start our session now. The, Today's session is about induction heating and how you can improve the efficiency and the power, increase the power of your induction heating device, whether it's used for industrial or domestic application. Let's see our agenda for today's webinar. In today's session, we'll talk a little about induction heating and its main application. EMWorks solution, we will show you our proposed solution that can be used as a virtual prototype platform to simulate and validate your design for induction heating related applications. Then a quick live demo of EMWorks, our proposed solution. And later on, we will tackle a case study which is about induction hardening of a gear, a mechanical gear. Then we end our session by conclusion and a QA session. So let's start. Then, as you know, induction heating is efficient, reliable technology for energy transmission. It's used by injecting a current, high frequency current in a coil, and that high frequency current is going to induce eddy currents through the magnetic fields in a workpiece. So you have a heated piece or workpiece that will receive the induced current, and this induced current is going to generate the heat. So the heat is going to be created by the induced eddy currents on a conductive and magnetic workpiece. So it's efficient. It can provide more control on the heating process, heating time, and power. So you can adjust the power by adjusting the current or the voltage of your coil, induction coil. Also the time, so you can also customize the heating time and so on. It's localized. It's localized, so it's gonna heat only the workpiece. So you have any other like maybe surrounding, maybe parts or ceramic or whatever, it's not going to be heated because they are not conductive or metallic components. So it's gonna heat only conductive magnetic components. So it's localized, fast, and precise. So it's fast because it doesn't go through different layers of components. It's directly go to the workpiece, to your heated piece. So it's a clean and safe and so on. So these are the main advantages of induction heating, and it's widely used in several fields. So as you can see, something I mean implemented of the induction heating process in NDT. So it's used for NDT applications. So it's gonna heat plate, a plate that we want to investigate, and then because of that, maybe induced eddy currents, we will be able to identify maybe some hotspots due to the cracks or any other defects on a plate. And this is again is induction heating principle. So it's used for NDT applications, for thermoforming molds, and other industrial application like hardening, tempering, melting, and so on. For domestic application, it's widely used for induction cooking, which is an attractive application. So it's used for cooking systems, and it becomes more and more common in our houses. Also for medical applications like hardening surgical blades, brazing steel parts, and so on. So induction heating is a process, is a physical principle that is applied in several applications, and it's, as we mentioned, it provides several advantages, like it's a safe, clean, and efficient process. So in order to provide more efficient induction heating, on which you have more control on the temperature, the heat profile. So you have to, maybe in a certain application, you need to generate a certain heat profile. So you have to maybe generate heat in a certain position, a certain area of your maybe application or heated piece. The heating time, more control on the heating time, improve the efficiency. It's already this induction heating comes with higher efficiency compared to other applications, but we can improve the efficiency. Also, we have to investigate or tackle EMI, EMC. We have to look at the EMI. So we have to make sure that our induction heating application doesn't generate a lot of fields around the device. We have to respect some standards. So we have to limit the radiation of the electromagnetic fields to avoid any issues related to maybe some human body, also some other electronic devices. Thermal and EM stresses. So you have to look at the thermal. So you have to limit the thermal in area that you should not see a lot of heat. So you have to also reduce the heat. So it's not the heat that we generate in the workpiece, but heat that may be generated in other, might be the electronic system, like the power supply and so on of your device. And stresses. So because you have heat, you should get more thermal stress, and also the stress is due to the Lorentz force that is generated because of the eddy currents. For this purpose, so you can investigate the inductor design. So you have to maybe evaluate your inductor design, the shape, the number of turns of the coil. So the inductor is the coil or set of coils. It can be coil or several coils. So the shape of the coil, the number of turns that is used in your coil, and the position. So you have to look at the position of the coil. So to generate efficient heat or efficient maybe heating process, and respect EMI, EMC, respect other like criterion like maybe some heat profile, precise heat profile, heating time that you need to respect certain time to heat your objects. Also additional maybe field shaper, so you can use the additional field shaper to improve and localize further the heating process. So these kind of things that you can maybe tackle while designing an induction heating. Also the workpiece. So in case, for example, induction maybe cooking applications, so you can maybe work to optimize certain maybe pots or pans that can be used for uh, these induction cooking devices. So you have to maybe look at the geometry, the shape of the heated piece, and so on. So you have to maybe choose certain geometry, certain design of the workpiece. For this, as you can see, so these are the factors that also you can play with. So the frequency, so you have to adjust maybe the frequency to decrease or increase the heating. Also the materials, so you have to try different materials to find out which is the best material for application, magnetic, non-magnetic. Also you can, for a more realistic analysis, you can use let's say, temperature dependency in your material. So you have to use some materials that are temperature dependent, like the conductivity, resistivity. We know that the material property changes a lot with the temperature. So you have to include this in your analysis or your design process. And input power, of course. So the input power, and with respect to your coil. So you don't, you increase the power up to certain level. So you have to maintain a low temperature for your coil. Also designing some cooling system as well can be also part of this design cycle. And the speed, in some application we use speeds, whether it's rotating or maybe for like our induction hardening is rotation, but for the other application it can be translation. So we can investigate the impact of the speed on our heating process, because moving an electromagnetic field is gonna generate additional eddy currents, but they can they can be negligible compared to the heat that is generated by the time varying field itself. So in this context, we'll go through few applications that are were solved using our solution. So our solution is used for this kind of application, and it is validated. So we can see here a thermal simulation of a mold, temperature and used heating. So we can see the heat generated in the mold. So as you can see here, this is the heat in this top face here. So it ranges between 46 C and 128 degrees C. So this is the range of the heat, and you see the heat. So with some more, you can optimize further the heat profile, the heat distribution in your workpiece. Also, a validation against experimental provided by our reference. So this is the reference that you see at the bottom of the slide. So you can see the variation of the temperature versus time, and the validation of EMS, our solution, our software, against the experimental data. So you can see that the temperature increases from 40 up to 80, so 80 C, and after 15 seconds, and up in a certain point. So this is a certain point. It's not the overall temperature in a specific point. All right. Let's see another example. These are another. This is another example. So it's an electromagnetic mold with different coil shapes. So here, the author investigated the use of different coils, different coil structure, and see their impact on the results or on the heat. So as you can see in this graph, so you can see that the temperature is higher. If we see the left graph, the left figure is higher by reaching a value of 100 C, but it's very local temperature. But the overall temperature is around 90, 100 maybe in the system. While in the right, we can see more distribution across your heated piece. So we can see some more uniform distribution. It's better distributed, the heat in the second case, in the 2D coil. It's called a 2D coil. So this is the heat, this is the transient temperature after 2 seconds. And we can see the table that contains comparative data between EMS and some reference results. So there are like some simulation provided results and experimental results. And we see very good correlation between our solution, between our software and other like simulation and experimental. So another example that uses a different kind of simulation, which is the transit simulation. The ones that we saw in the previous slides were like using frequency domain simulation, which is powered by a sinusoidal, pure sinusoidal excitation. So it's steady state. Here we must use transient because we have a specific excitation shape. We can see the current we form here. So we have a specific excitation shape, and we have to use a transient and then import this excitation. So you can import your excitation. So we can maybe create your excitation in a separate tool and import it to the software, and then run your analysis. So this is the excitation that we use it for the coil, and this is the current distribution. We can see the eddy current distribution here in the heated piece, and here we can see the temperature. So the temperature is reaching some values around 692 C, and the overall is around maybe 500 something degrees C. And this is another validation example that is used to validate the data, to validate the analysis of such application using our solution. So let's see our solution in its platform. Inside Autodesk Inventor here. So our electromagnetic software or our electromagnetic solution is CAD integrated inside Autodesk Inventor and SolidWorks. So here we are in this session, we are looking at Autodesk Inventor. So you use Autodesk Inventor for the CAD modeling. So you draw your CAD, you create your CAD using Autodesk Inventor, and without exporting any geometry, you can do your electromagnetic simulation, your complete electromagnetic simulation. You can transform your Autodesk Inventor into virtual prototype platform for electromagnetic design. So whatever application related to electrical engineering or electrical devices, you can use the software, you can use our solution to run your simulation. So it can be used in addition to induction heating, it can be used for other applications like maybe motors, it can be used for inductors, solenoids, wireless applications, also cables, fuses, and bus bars, and so many more applications. So it can be used to analyze, simulate different applications, from like DC application to a few megahertz application. We have also RF solution, is a different topic, but we can cover also high frequency analysis. So here you can see our example, our hardening example. This is the coil and this is the gear that we want to heat. Here, if you just switch from model to EMS feature manager, you switch from the CAD to the simulation. So without exiting this platform or this software, so you don't need to go outside. So you create this geometry that can be modified at any time. So you switch to the simulation. The simulation, as we will show here, you create your analysis. Analysis may be magnetostatic. Magnetostatic is for magnetic field calculation in a DC. So you use this for permanent magnet application, for DC powered coils and so on. So you can use this magnetostatic to compute torque, forces, DC resistance, inductances, and so on. Electrostatic for DC electric field calculation. So you use it for maybe cables to evaluate some dielectric failures, some breakdown, you evaluate electric field distribution, radiation, EMI, EMC, and so on. Electric conduction, so you put your current, see the current distribution across your system for bus bars or any other like applications, for example, fuses, MEMS application, and so on. AC magnetic is a frequency domain simulation for magnetic field calculation. It can be used as well for induction heating process. So you can specify the frequency. So it's a frequency domain. It's not time domain. So you can specify the frequency and run your simulation to get losses. I mean, in addition to the magnetic fields and so on, you can get AC resistance, inductance, impedance, back EMF, and so on. And the losses. Losses may include the solid loss, or let's say eddy current losses, ohmic losses, core loss, and these kind of all type of electromagnetic losses. Transit is a time domain simulation solver for magnetic fields, so you can apply whatever shape, whatever excitation shape, and like AC magnetic, on which you can only use, I mean, it considers only sinusoidal excitation, but here you can use sinusoidal, you can use a pulse, you can use any random excitation shape, also DC and so on. So they can be used in this analysis, and it's gonna give you the results similar to the AC magnetic, but in versus time. So you look the results at your results versus time. AC electric is similar to the electrostatic, but in the frequency domain. It's something also similar to the AC magnetic, but for electric field calculation. So you can specify your voltage, current at a specific frequency and get electric fields and, let's say, breakdown, voltage, dielectric failures, uh, voltage distribution, capacitance. You can compute capacitance as well, and also you can compute losses in dielectrics. All right. So in addition to these analysis, you can also couple your simulation to thermal, so to get the heat. So you have losses in your electromagnetic device, which are computed by the software. and those losses are dissipated as heat. So you have to compute, estimate the heat, especially for induction heating application. You need to look at the heat. So, and this temperature or thermal coupling can be like steady state or transient. Steady state is just one final quantity, doesn't go through time to get to the final temperature. It's just one shot value. And transient is like time domain simulation for thermal. So you can do like AC magnetic is a steady state magnetic solver plus a transient thermal. So it's going to use the losses, electromagnetic losses, which could be ohmic loss, eddy current loss for your induction process, uh, core loss, and so on, and generate, compute the heat versus time. And you don't need to like export any losses. So automatically those losses in the electromagnetic side is going to be used as a load for your thermal simulation. Later on, you can define additional boundary conditions. So you can set like some predefined temperature and maybe some other additional volume heat, but mainly the heat or the loss map is going to be automatically and internally communicated from the magnetic solver to the thermal solver. So once you create a study, so you get your study which contains the materials. So your materials here, you can see the materials. This is the gear, and this is the coil, and this is like simulation medium is the air. So you define your materials. The materials available in the library that comes with the software. So as you can see, this is the library, and it's a rich library. So you can choose most of the available or commonly used materials from this library, apply it to your, sorry, this is not made of copper, but maybe some stainless steel. Let's say stainless steel. So you can apply stainless steel, apply copper to your coil. So, but this library also can be customized. So you can modify the properties. So the properties that are available there can be modified. So you can change conductivity, for example. Maybe your supplier has a different material property. You can change this through the library, or you can add your own material. So you can customize the library in a different way. So you can change the properties of existing materials or modify or add your own stuff there. Also, it can be used like to apply to add temperature dependent material, which is an important parameter in for more realistic simulation. So you can apply, for example, conductivity versus temperature, which is a curve like this. So it's gonna be like dropping like this because resistivity increases, and here we define conductivities. Okay, so once you define the materials, next step is boundary condition. So you don't need anything here, but when doing thermal, you just this is a thermal couplet simulation. So you only need to specify convection here for your material setup. So here we will use the air as for the heat or for the convection coefficient. So apply, as you can see, you can load the list of the materials here. So apply, so it's gonna apply there, stop, so we can keep using the default settings. After you finish this boundary condition, so you don't need to apply tangential normal. So well, tangential sometimes it's needed, but for thermal inputs, you only mainly need convection. But if you wanna add additional boundary condition, yes, you can do thermal, you can apply heat flux, radiation, and volume heat. It's a power per volume or per cubic meter. So then once you do that, you define a coil. Coil can be wound or can be solid. Solid is like our case here. So you just select this coil, then go and specify, let's say, entry ports here, exit port from this side, and current and phase. So you put, for example, 1000 amp, RMS, and that's all. So this is what you need to specify. So if you have, let's say, coil with a set of number of turns, like you have a cylinder and you want to define number of turns, so also it's possible. So we have the wire diameter or the wire gauge and the number of turns. So we can specify the number of turns as well. For other like platform, it's gonna like SolidWorks, we also provide the leads wire definition, and it's gonna be available in Autodesk Inventor solution and also in our standard solution, which is coming very soon. All right, so these are like the main steps. Mesh, you can use the default mesh, and these are the main steps to get your results. I mean, after running the simulation, of course. So you just run this simulation and to get your results. I have also already solved the study, so to avoid some time in running this. It's not going to take a lot of time, but it's like a couple of minutes. Okay, so you see this is the same definition, the same setup, and now we see the results. The results table may contain different like inputs or different results like the inductance, resistance, impedance, and so on. So these are results that you can see here. So we have the impedance of your coil. Also, you can see the losses. So this is the power. So we have 1.7 kilowatt in our coil, and we have a total of 5.5 kilowatt in the gear and the heated piece. Okay, you can look at the field distribution. I mean, the 3D plots, it includes magnetic flux, magnetic field H, applied current density, the current density, the overall current density, which includes the applied plus the induced eddy currents, force, electric field loss density, and temperature. So these are the magnetic results, and these are the temperature results. Here you can see, so for example, you can just plot this temperature. So double click on this, and these like plots can be like a vector, can be line, can be field lines, can be also in a cross section, and so on. So you can plot these different fields. So here you can see the field distribution. And if we look at the current, let's use one section plot here. So you see the field distribution here, the eddy currents vectors there. And the temperature, so we can look at the temperature as well. So the temperature due to electromagnetic losses. So we can see the temperature that went up to 1,200 degrees C in the gear, and there are some hot spots in the gears here. So yeah, this is from like platform point. So this is the software. So if you once you finish, for example, this analysis and you wanna try some other options, you can go back to the model, change it, modify the shape, modify some dimension, and so on, get back again to the simulation, just update and run again. So there is one option that can help also in this kind of like what if analysis is the parametric simulation here. So this parameterization can help you to parameterize both geometrical and simulation variables. So you can parameterize current, voltage, frequency, and you can parameterize any geometrical dimension in your system, whether it's like sketch dimension, a thickness of a part, a distance between parts. So these kind of things can be parameterized, and you'll be able to see the results versus different scenario. The scenario means that you have a value or a parameter or combination of different or several variables or several parameters. All right, so let's get back to our presentation. So our case study for today is an induction hardening of a gear system. So we'll investigate, or first let's see, I mean, the advantage. So it's fast heating, so the short cycle of time. So the induction heating is known for its fast heating. It can be applied for internal or external surfaces. So you can apply it for like the outer faces of your system or the inner one. So it's flexible process. Uh, it's selective, so you can have a lot of control on the local or the localization of your heated areas or parts of your device. So you can create some residue without affecting other parts. So you just target only one piece or one part of your uh, components. So it's easy controlled induction. So it's based on some no limitation for higher profile or workpiece. So you don't have any for hardening profile and so on. So you don't have any limitation on these things. It's an advantage. It's a great like application of induction heating phenomenon. So if we move now, so we have our tested case. These are the properties, the design data. So we have the module, and have the number of teeth is 9, some optimal frequency. So the common used frequency is between 20 and 40 kilohertz. The skin depth, I mean, the skin depth is known for eddy currents related phenomena. So we have this kind of skin depth ranges from 2.9 millimeter to 2.2 millimeter. And material, so here we are using steel 304 for the gear. Okay, so today we'll investigate 3 options for the coil and see what is the best heat that we can get. So we have like a multi-turn coil, we have cylindrical coil, we have an open cylindrical coil. So we'll start by number 3. So this is the open coil. So it's tested, and it's, you know, that it's pretty flexible and easy to test these combinations or this configuration inside Autodesk Converter. So you just switch from a design to another design without closing the model. So you can have all of them inside one design or using one model. So we have the design one. You see the current distribution and the heat. So we have slightly asymmetric heat. So we have some red here, as you can see, and it's just yellow in the other side. So it's slightly asymmetric heat. Also, you see that the current is a bit symmetric, but it's something very local. So it's maybe higher current distribution from left compared to the right. Okay, the current that is used is 4 kilo amp, frequency 30. The heating time is 5 seconds. So we have this also design. Now we can see the current distribution is more and more uniform or and symmetric. Also the heat, so it's pretty symmetric, is a nice distribution. And for the third, the multi-turn is also asymmetric. It's even worse compared to the first case. So we have more asymmetric behavior, but we use less power here, as you can see. So there are like different different trade-offs that we can look at. So another thing that we can see is the dependency of the heat, or the relation between the frequency and your generated power. So we can see that here, this is the frequency, how the frequency affects the skin depth. So the skin depth decreases, so became smaller when you increase the frequency. They are like anti-proportional. So the frequency and the skin depth, the power increases with the frequency. So the frequency, for example, at 25 kilohertz, you get only 4 kilowatts. But if you go up to 100 kilohertz, you reach 12 and more, or 13,000 kilowatts, 13 kilowatts. So we can generate more power by increasing the frequency. But this is gonna also affect your coil. So it's gonna affect maybe the efficiency. So here it's the solid loss, or the induced eddy current loss in power per cubic meter variation across your gear tooth. So it's just in this line from A to B. So you can see the variation versus different applied frequency. So it increases when you use higher frequency, as can be shown here. And it shows that there is like more maybe localized but symmetric phenomena here. So another investigation is the temperature here. So we can see the temperature versus the frequency. So the temperature at 25 kilohertz is around 700 C, while it reaches 3,000, more than 3,000 C in 100 kilohertz, which is unnecessary temperature. So for other like situation where we can investigate the heat, I mean, when using some thermal dependent properties. So we can see here that we are using thermal conductivity versus time, and we can see the difference between using just a linear constant thermal property that doesn't depend on temperature compared to more realistic temperature. So we can also go and test this case by applying thermal or any other property, thermal conductivity or electrical conductivity or specific heat versus temperature. So we can see the variation now of the temperature versus time. So for nonlinear thermal conductivity. So when it's used, so we can see this variation here, and the temperature here along like between 2 points here. So here it shows the difference in temperature. So there is like more uniform, I mean, temperature after certain distance here. Yeah, so finally we come to our conclusion. So different aspects of induction heating. So we're addressed today. So we saw how EMWorks solution can help you to design and improve the efficiency of your system by trying different coil designs, by changing the frequency. You can see what power you can generate also by using a temperature dependent properties. You can also change the current. You can change also the distance between the coil and the heated piece and so on. This kind of things can help you to optimize and improve the efficiency of your induction heating related application, as we saw that is applied in several fields like industrial application, domestic application, also medical applications as well. So the integration of our solution allows for a better like design cycle. So you can use the power of the CAD. So you can design whatever idea in your mind inside the CAD. This is a professional CAD. Autodesk Inventor is powerful CAD. SolidWorks is also powerful CAD, and even our standalone solution that will come soon is powered by Autodesk Inventor. So it's gonna be integrated with SolidWorks. Autodesk Inventor, but it's EMWorks product, is EMWorks studio or solution or platform. So you can also we also showed the accuracy, the reliable results we can get from our solution. So we compared the solution, our results, to both other like third-party tools provided by references, articles, also by experimental data also available in these references. So the results were showing very good agreement. So you can do some also optimization of your design. So we have our automatic optimizations that will be available very soon as well. So it's a single platform, it's a unique platform for electromagnetic multiphysics simulation. We also do the NVH in SolidWorks, and it's going to be also available in our standalone solution. So yeah, this is overall for today. Please feel free to type your question in the chat box, and we'll be happy to answer them, whether in this session now shortly or through emails. Thank you all for your time, and hope we see you again in other sessions.